Hi, welcome to our Senior Capstone Design Expo. We are Team VisceReal. My name is Diego Gatica.
My name is Lucia.
Hi, my name is Hudson Mckinley.
And my name is Mostafa Meselhe.
We got the idea for our project after meeting with Dr. Chrissy, a surgeon at Tulane Medical Center, and we realized that surgeons and medical professionals can't properly practice emergency procedures for patients with penetrating trauma to the thoracic and cardiac regions. These surgeries are high risk and infrequent, which makes it really difficult for residents and unexperienced surgeons to learn how to properly practice on these. Our need statement is that medical professionals teaching and learning emergency surgery need an accurate simulation device with reusable and consumable components for penetrating trauma to the thoracic and cardiac regions. While brainstorming, we thought about the different functional requirements that our model would need to serve, like the anatomy of the heart, blood flow, strong beating, reusable, whether there's coronaries present or not, ease of setup, and realistic material properties. After discussing the different requirements and meeting with Dr. Guidry as well as a cardiac surgeon from Ochsner, we then decided that the most important aspects for us to address were the strong beating and the blood flow and bleeding aspect of the model. We then brainstormed different solutions to create the beating aspect of the model, such as a pressure-driven beat, a claw that would actually compress the model, or even an electroactive polymer casting. And to decide which solution we wanted to pursue, we created a pew chart to quantify the pros and cons of each of the solutions. We ended up deciding on using an electroactive polymer casting. However, after further research, we'd realized that the polymer wouldn't be able to electrically compress and release to simulate the heartbeat fast enough. So instead, we decided to do an integrated solution with the claw, our second best solution on the pew chart, and actually cast the claw into the polymer and have it be mechanically induced.
Next, we have our block diagram and the parts of the solution. So for our heart model, there are really three primary components: a beating, bleeding, and anatomical component. For the beating, we have the contraction, which is driven by a string and motor assembly, and the torquing, which is contributed by a mechanical arm. The bleeding will be moved around by a pump system and a blood analog, which will fill the pump system at a velocity that will kind of ooze out of the heart but not project itself out of the heart. And for the anatomical component, we have the material properties, which is the elasticity and shear strength, which we satisfied by finding a silicon compound called dragon skin that's been proposed to have similar properties to muscle tissue in humans. And the coronaries, which are the elastic and have an indicator that indicates incision. Next, we have our business model canvas, which sets a few of our key partners, key activities, our value proposition, customer relationships, and such. It's not too important, but we just thought we would include it. And then next, we have our design traceability matrix, which has our user needs, design inputs, our design outputs, and design verification. So an example of this would be our strong beating that we need to simulate the real-life scenario of cardiac or thoracic puncture wounds. We will input this via a mechanically induced beating system. We'll output via a motor rotating wheel attached to a windshield wiper style motor, which will pull and relax on a silicon model as the motor rotates. We will verify this design by extensive testing on speed and force based on the silicon resistance, and we will validate this on user feedback of the strength and feedback from the meeting of medical professionals with previous experience with cardiac or thoracic puncture wound scenarios. And here are two more user needs: the accurate simulation of material properties and controllable aspects of the training by the technician, as you can see on the slides, with additional inputs, outputs, verification, and validation.
Evolution of design. This is prototype 1, which was the product of a rapid prototyping session in class, and it consisted of a heart model made mainly out of foam with coronary arteries modeled with drinking straws. And this prototype allowed us to display a physical representation of what we wanted our product to be. This is prototype 2. It is a hollow silicone rubber hemisphere made out of UMU 30 silicone rubber. It has a string attached to mechanically induced beating, as you can see in the following videos. So in the video, you can see the mechanically induced beating. And in the second video, you can see the same beating, but with a puncture wound, which is meant to simulate the puncture wound to the cardiac thoracic area, which we identified in our needs statement. This is prototype 3. It had a diameter twice as large as the previous prototypes, and the purpose of this scaling up was to approximate the size of an organic human heart. So this is our current prototype. it has 3 points of attachment for the string for the mechanically induced beating, as opposed to 1, which was the number the previous prototypes had. And these 3 points of attachment help with load distribution across a larger area of the prototype. So this helps with resistance, for example, so it doesn't tear as easily because the force is not concentrated just on one area. It also comes with a puncture wound pre-made into the model and inlet and outlet holes for artificial blood flow through the model. This is a video demonstration of the functionality of our current prototype. It is within a body cavity, and this is meant to simulate cardiac/thoracic puncture wound surgery. And you can observe the mechanically induced beating within the approximate anatomical context.
So now to cover our testing protocols, Protocol 1 is a test for the compressibility of the materials that we were using. This was a compression test that is performed on a cube of known dimensions, where the material was the silicone rubber that we were using in our prototypes. This rubber is an Umu brand 2-part mixing rubber. It's a very basic rubber, but we wanted to be able to test it to see how accurately it represented cardiac tissue. This test involved lowering the top arm of the ADMET machine onto the superior surface of the cube, and then testing that compression with the ADMET software at 10% per minute strain rate, 50% per minute strain rate, and 100% per minute strain rate. Protocol 2 was a deformation testing protocol, where the objective was to measure the amount of force to achieve a desired displacement of the silicone rubber heart model. This was because the goal of VisceReal was to gain a very accurate displacement, a sizable beat that surgeons can practice on. To measure the deformation as displacement when beating, we would use a digital height gauge. This would involve lowering the gauge onto the top surface of the mold, engaging the actuation for beating, and then measuring that displacement using that digital height gauge. We also performed digital simulation testing using SolidWorks. This involved importing a step model of our mold and then applying force to it so that way we could measure the displacement and von Mises stresses that formed in the mold. We rendered this with an orthographic and a side view. Our future plans involve more accurately matching the tissue properties of the heart. We purchased Dragon Skin brand rubber, which more accurately mimics the tissue properties of the native muscle tissue, and we plan to use this. We're very excited to see where that takes us. We're also going to add a pump to simulate the blood supply in the model. Unfortunately, due to coronavirus canceling in-person classes, we didn't have enough time to add the pump to supply blood to the model. However, we do have the pump and we're excited to do that in the future. Lastly, we're very excited to test the device with healthcare professionals. We'd like to be able to bring it into real surgeons so that way they can practice using the device. Team VisceReal would also like to appreciate those who provided funding, including the Tulane Department of Biomedical Engineering, the David A. Rice Design Endowed Fund, the Tulane Biomedical Innovation for Global Impact, and NIH Grant 5R25EB019904. Lastly, we'd like to recognize our peers and their profound work. We're very excited to graduate with them.